Hello, my name is Zhong Lin Wang from Georgia Tech. I'm going to lecture on piezotronics, a field we created in 2006. Piezotronics, what is it about? What we can do? If you look at this technology development, there's many things associated with daily life. Example, that most will drive the speed, make the device smaller, faster. But today, with more personal, portable, and polymer electronics, people look at functionality. So anywhere with speed and functionality, drive into a smart system and a solar power system in a different direction. This is what we're looking at. When we look at a smart system, we definitely have human-machine interface. How do we interface a human with a machine? Those operate in different mechanisms, different physics here. How do we interface? Well, silicon electronics work on semiconductor physics. Human work on mechanization. When you interface them, how do you do that? Early days, we demonstrated piezoelectric nanogel using piezoelectric materials. The idea is on the mechanical strain, polar charge created at the two ends of the nanowires. This can be a driver force for the electron to flow in the external loads, back and forth, if you have a block layer which prohibits the electron flow through the wire. So this is the driving force, and this is nanogenerate. Now let's change a bit. Let's say instead of get rid of this block layer here, so the electron can go through. On the mechanical strain, polar charge created. The polar charge can tune the transport of the charge carriers inside these semiconductor materials under the driving of the external voltage. This voltage drives the transport of the carrier here. But the presence of the polar charge here can greatly control the way the carrier flows through the interface. This is the core of piezotronics. Mechanical agitation produces the piezoelectric charge to tune the carrier transport process is the fundamental of piezotronics. We create this field with this analogy. Coupling between semiconductor, piezoelectricity, and photoexcitation give you a few number of exciting areas. We are well known that optoelectronics is the fundamental of today's many technology. Here we produce the piezotronics, which is this coupling between semiconductor and the piezoelectricity. The fundamental physics lie at the interface of polar charge to the carrier transport process across a PN junction or across Schottky contact. The first time we introduced this phrase was 2007, nano piezotronics, and this is today's very popular effect. It's a fundamental physics effect and can be applied for many different purposes. This is a simple case. Look at the solid-state transistor. We have a source, we have a drain, have a channel. And the gate is controlled the channel width so that the current from the source drain can be controlled. So this is the fundamental. You control the channel width. Instead of controlling channel width, we can control the interface at which the charge will flow. And this idea is that regardless of the width of the channel, if we control the interface at which the carrier flows through here, this is a control. Same like this does. This controls the channel width, this controls the exit phase. You'll be able to control from tensile strain, and you can compress the strain, so the polar direction of the polar piezoelectric charge reverses. It's positive here, it's positive here. Then you can control the left-hand side or right-hand side of the device, depends what the strain you apply, the strain-gated transistor. Let's look at a simple analogy here. We have a metal semiconductor contact. Metal semiconductor contact is such a case. When we form an interface, we can form a Schottky contact. With the Schottky contact, we have a barrier. If this side is piezoelectric and semiconductor, on the mechanical strain, polar charge created. Negative ion, raise the barrier height. If you reverse the strain, positive ion at the interface, lower the barrier height. This is raised or lower barrier height at the interface can gigantically change the transport of charge across the interface because it is exponential control. It's not a linear control. You can turn it on and turn it off, just simply by this polar charge at the interface. So this is the fundamental of piezotronic effect for metal semiconductor contact. If you make a single nanowire device, the two ends have contact. Shorty counter here, shorty counter here. Now, it is the polar direction here. Let's measure it. You apply a bias. Bias shifts the two Fermi level from this side and this side by the voltage you apply. In such a case, if you, in addition to voltage you apply a tensile strength, we can create a positive polar charge here, negative polar charge here, and then this positive voltage here lower the local barrier here. Lower the local barrier here, help the electron flows like this. Lower the barrier, the electron flow like this. Lower the barrier, the electron can flow easily here. That's why on the tensile strain, you have its device on. When changing tensile strain to compressed strain, the lower voltage on this side, low voltage side here, raise the barrier height. So electron flow like this, cut it off. So on the compressed strain here, it is off. So this on-off can be a few hundred to a few thousands ratio. This is a strain controlled transistor. Used to be this gate voltage, the strain gated transistor. This is the basic of this piezotronic transistor. So this is the lateral device. If you look at the extreme case, the first time we demonstrated this one was use a single bonded wire here on the tensile strain, on the compressor strain. On the tensile strain, you can see the change. The dark curve was the original MV curve. On the tensile strain, the red curve is dialed this way. On the compressor strain, the green curve is dialed this way. Green and red are two reverse polarity. Why is this? It's because the polar charge here to the barrier height and the mechanism proposed in our two important papers, the nano letters in 2008. And theoretically, we also worked it out. Besides, if you have a PA junction here, this is the driving force for the voltage return. But this is the piezoelectric curve. You see, this is a positive quantity, but this can be positive and negative. If you have a positive piezo charge here, this is a positive quantity. Exponential positive number is enlargement, magnification. So large current can go through. But if you become negative current, this is exponential of a negative number. It becomes extremely small. It's cut the current off. This is a strain-gated transistor from a simple equation point of understanding. So if we can make this kind of contact, we can tune the piezoelectric and tune the device. We can make a source, a drain. On one flat substrate, the top and the bottom can form logic computation. And you can connect the right away, you'll be able to perform strain-controlled logic computation. For example, you can use strain to control rather than the voltage control. And this kind of similar like conventional logic computation, but it is piezotronic logic computation. You can do many kind of simple logic calculations based on our piezotronic transistors. We not only make the lateral devices, we make a vertical device. This is the vertical device here. Vertical device. You can see that this vertical device, when you apply mechanical strain here, mechanical force here, you can produce the polar charge here. The presence of polar charge change the barriers when the carrier flow through here. We can shift the turn-on voltage to a higher value. As you see experimentally here, when the force increases from 420 nanonewton to 700 nanonewton, you can see the turn-on voltage increase from half volts to about 1.5 volts. If you fix it at 1 volt here, 1 volt here, this is on, this is off. Strain-gated switch. Strain-gated switch. So this is the basic of one device. Now, if you can have an array of devices, for example, classical semiconductor have the source and drain, and gate. The gate is giving you occupied space. If you can't get rid of gate, this cannot be built array. So therefore, this package has to all go through the top. In such a case, if you get rid of this gate electrode, use the internal field to replace it, you can have a new transistor called piezotronic transistor, 2 leads. If this is possible, you can build a crossbar electrode. You can have many of this one built based on this. We have fabricated a chip. This is called piezotronic transistor array chip. On 1 centimeter areas, here we have the device inside nanowires, electrode, packaging material, filling materials. Totally take 31 steps from nanowire material sample preparation, nanowire growth, to device fabrication to packaging. This is a piezotronic chip. Now let's look how this works. Let's analyze 92 of these channels. 92 of this transistor across this way, 92 this way. We can measure the transport on the fixed bias. You can see the current like this. Now if you apply a local strain here, you can produce tuning. This changed current gives you the signal. But this can be 2 effects. One can be piezo-resistant effect, can be also piezotronic effect. Which is which? I want to show you this is the piezotronic effect. Why? If you measure the whole 92 here, you have 92 this way, 92 this way. Over the 8,000 of piezotronic transistors give you a map or image. Okay? Why is this a piezotronic effect instead of piezo-resistant effect? Let's look at the measurement. This is associated with 1 pixel, sweeping the bias from reverse bias to positive bias. Let's see the current change. Before we apply a pressure, after we apply the pressure, let's see the change. Before we apply the pressure, you measure the transport when you're sweeping the bias from reverse bias to positive bias. Now, after you apply pressure, let's compare. On the positive bias, this was the current. After you apply the pressure, this was the current. Current reduces at the positive bias. But look at the current here. This is the reverse bias, increases. On the reverse, the current increases. On the forward, it drops. This is the asymmetric change. It's because the asymmetric distribution charge, the 2 ends here, depend. This is non-symmetric. Which way the current flow depends the local polar charge sign here, which dictate the transport across this interface. And in such a case, you can manipulate the transport. You see, if you say this is forward bias, this is reverse bias, you change the barrier height differently, change the characteristic of the current. In such case, the electron goes like this. Lower the barrier, it will flow. But in this case, the barrier changes here. It's one go through as what's normally applied here. So the reverse current change behavior is the fundamental characteristic of piezotronic transistors. Okay? What's the difference from piezo-resistant effect? The piezo-resistant effect is such, regardless of positive bias or reverse bias, if the current drops, it drops both ways. This is called symmetric change. Symmetric change. So therefore, it's fundamentally different. It's a new effect, fundamentally different from piezo-resistant effect. We use first principle also calculate that. We have a silver, single-side silver. You can calculate the distribution of polar charge at the 2 interface here from first principle. But disregard these complicated curves. You can derive the change in Schottky barrier height. When the strain changes from compressive strain to positive strain, you can see the Schottky barrier at one contact drops, and the other contact increases. This in contrast change is the characteristic of piezotronic effect. Utilize this one, you can uniquely identify it is piezotronic rather than piezo-resistance effect. If you make an array 92 by 92, you can map the distribution of the force across the image. And you can have a character like this is A. You can clearly map its distribution in this piezotronic transistor array. So fundamental was the difference between piezotronic effect and piezo-resistant effect. Any semiconductor can have piezo-resistant effect. Piezotronic effect only for Wozart and zinc-Planck semiconductors. This don't have a linear curve. This have a non-linear curve and can be rectified. This have a symmetric effect. It's regardless of which way you apply the bias, it is symmetric. But this is called asymmetric. That means what? It does depend which way is have a positive polar charge, which way have a negative polar charge. It's asymmetric change. This asymmetric change is that if the barrier height raises at this end, will drop at this end. This is called asymmetric change. They have no polarity. This have a strong polarity. This is a volume effect. This is an interface effect. This cannot be a switch. It can only be a sensor. But this can be a switch. If it can be a switch, you can do logic computation. You can do circuits based on this. So piezotronic effect is a new effect. How do we see the relationship between the piezotronic transistors and the semiconductor FET? First one, this is external voltage control. This is inner crystal potential control. This relies on gate voltage, relies on strain producing inner crystal potential. This have 3 terminals, this have 2 terminals. This is silicon materials, this is Wozart-based materials. This can be operated very fast, this is operated slow, but in the kilohertz or megahertz range, or even slower. But for different applications, this is for computation, logic, and photonics, or this can have human environmental interfacing, sensors, methods, photonics, and many things. So therefore, both are complements and integration rather than replacing one with the other one. So this is how we view the relationship between piezotronic transistor and silicon FET. Piezotronic effect also in thin films. It does not have to be nano. It's a universal effect. We have effect P-type zinc oxide nanowires and antimonide doping. You can see when the doping level of antimonide increases zinc oxide from 0.2% to 2%. The growth rate changes dramatically, but it does show P-type characteristic. Here. And then you can see that inside the doping does not appear as a point doping, appears as a linear doping here, and more detail might possibly can be found in our publications here. The reason I want to show you this one, this can be also P-type materials, can be also piezotronic transistor here. This is the transport. The blue curve is the transport on the zero strain. Okay. Sorry, the dark curve. The dark curve is the zero strain. Sorry, this is dark curve. On the 0.76 tensile strain, you see the current increase to here, but at the reverse bias, it drops to here. This side increase, this side drops. Why so? It's because the different sign of polar charge appears at the 2 different ends, which can raise the barrier and lower the barrier for the P-type transport. This is a typical characteristic of piezotronic transistor in P-type materials. So it can be N-type or P-type material. Both have this characteristic. Can also be applied a range of semiconductors. Does not have to be zinc oxide. Gallium nitride, cadmium sulfide, cadmium selenide, and zinc and tin oxide. All these materials. If you look at the periodic table for the 2,6 compound semiconductor, all this material we have shown have a piezotronic effect. If you have a sample for those ones, you can study yourself. I bet they should have piezotronic effect. If you have 3 5 compound semiconductor, gallium nitride, indium nitride all have this effect. I bet those ones should also have a piezotronic effect. And if you have the sample, you can do study. I want to show you one more case for the 2D materials. Molybdenum disulfide can have piezoelectric and a piezotronic effect. If you look at the structure here, molybdenum disulfide for single atomic layer, if you call it unit cell, this is the unit cell, the center of cations and anions overlaps. But you stretch it or compress it from one direction, the center of the cations and anions polarizes, give you piezoelectricity. Different polar direction here. But if you have double layer, if you look at the projection here, this have central symmetry. This have no central symmetry here, and this have central symmetry here. This should not have a piezoelectric effect. And we first time proved molybdenum disulfide can be piezoelectric dependent on the number of layers. And we carefully transfer molybdenum disulfide on a substrate and use Raman spectroscopy and other techniques to determine the orientation of the sample. We can make the electrode here. And as you can see, we lay down on the substrate, we make the electrode here. If You plane the substrate here. This is on the tensile strain. Polar charge appears at the two ends here, and this is the electrode here. If such a case, they have a voltage drop here, but the resistance is high, so the electron will flow from the external load from here to balance the field here. You see a current. So this is called similar like the piezoelectric nanogenerator. Just use a single atomic. When you release, the electron flows back. You see an AC output. We measure for single atomic layer, 3 atomic layer, 5 atomic layer. You see clearly piezoelectric output of 2 layers, 4 layers, 6 layers, none. Prove the idea that this structure has central symmetry, this does not have central symmetry. So again, this is a typical nanoscale effect. An effect that only 1 or 3 atomic layer molybdenum sulfide should have. If you larger than that, you don't have this effect. So it's a typical nano effect. It can also have a piezotronic effect. If a single atomic layer molybdenum sulfide, if you have a 0 strain, the blue curve, on the 0.71% tensile strain, on the positive bias, the current increases. Here, the current drops. This asymmetric change is because the asymmetric size of the charge at the two ends here, and which contribute to this characteristic. Now, if you have 2 layers, double layers here, you should not even have a piezotronic effect. This blue curve was the 0% strain. On the 0.76% tensile strain, this current increase on the forward bias. On the reverse bias is also increased. This is called symmetric change. This is typical piezo-resistant effect. This is typical piezotronic effect for 2D materials. And this can expand to many systems in the 2D materials. It can have an interesting implication for in addition to the electronic photonic effect. So we show the piezotronic effect, which is a coupling between semiconductor and piezoelectricity, which is one of these areas we have been developing since 2006 to today. We have done numerous things associated with that, and I'll leave that to future lectures or so. So I hope, what is piezotronics? Piezotronics is an effect that utilizes piezoelectric charge at an interface that can control the carrier transport. You switch, we can fabricate circuits, logic computation as a switch. More detail can be found in a book I wrote a few years ago for piezotronics and piezophotonics by Springer, and for the fundamental of piezotronics and piezophotonics. Thank you very much, and I hope this provides something useful for the piezotronics areas, and anybody have an interest in that, feel free to contact us. Thank you.